Okay, so today and tomorrow we will be talking about this disjoint set data structure. We also call that union find. And as such, the actual use case of this data structure will come in the next week. So when there will be some greedy algorithms on graphs, so specifically there will be a Kruskal's algorithm where you will need this data structure. But today today and tomorrow I will discuss that independently of that problem. Okay. So yeah, this you will get to know in the next week, but let's discuss about it independently of that problem. So that also gives me some time to talk about a concept called something called an abstract data type. So uh, what do I mean by an abstract data type? And yeah, so I will introduce this as an abstract data type, and then we will discuss about the implementation view. So what do I mean by an abstract data type? See, why do you need to use uh, different types of data types? Why do I need to study different types of data structures? What is the need? Why can't I do everything with array?
To organize the input
To
in a
I'm
design
sorry?
efficient
way.
algorithms.
What you're saying, yes. For designing your algorithms, let's say a particular algorithm, you will have to do certain operations. So you will see, oh, I need certain operations to make my algorithm efficient. So you need certain operations. Okay, and what you do, you have an operational view first of all. So you have an operational view. So I'm calling implementation view an operational view. Operational view means, okay, what exactly do I need, right? What operations do I need? For example, like things that you have used earlier, like say stacks or queues. So you have an operational view that, okay, I need a data structure where, okay, I can store some elements and I put them on top of the element. Whenever a new element arrives, I put it on the top, and whenever I have to remove, I remove it from the top. Okay, and I need some functions to check, oh, are there any elements at all, or what is the element at the top. So I need certain operations. So I say, okay, I need certain operations, like I want to push an element, I want to pop an element, I want to see the top, or I want to see is it empty or not. So you see that, oh, I need certain operations. And similar thing you can see with queues. For queues also you have similar type of operations that are defined. And you say, okay, if I can use a data structure that supports all these operations, my algorithm will be more efficient. Okay, so you say, okay, if you give me all these operations, I can run my algorithm efficiently. That is the operational view. And there is a second view called implementation view. In implementation view, what you will see, okay, I have to you do stacks. Now, how will I actually implement it? Is there a single way to implement stacks? You know at least two ways, right? I can use simple arrays, I can use linked list. So you see, for the same operations you want to support, there are at least two operational views. to implementation view, that I can implement using either arrays, using linked list. Right? And ideally, what you want, so as a programmer or as a user, uh, you want to focus more on the operational view. That is where you have all these interfaces that, okay, I just want to use stacks. I don't care so much how this is implemented, but let me use stacks. Okay, so you want to know what are the operations. You want to know what are the operations I want to use. Okay, and then there's an implementation view that generally you want to avoid. Oh, okay, fine, it is implemented somewhere. Yes, I need to use that. Of course, you will see that is also important, because how it is implemented will also determine what is the complexity of various operations. But in general, if you want to just you want to be a user of data structure, you can. You just need to know the operations that it supports, and that also helps in making it modular. That okay, I have my ADT implemented in some way. I have the interfaces. I know how to use that, and I use that. But of course, in this course, in this lab, we try to give you both. You not only have the operational view, you also see how to implement that. Right? But yeah, I think after some point of time, you will not worry too much about implementation view, unless you have to define your own new ADT. If you have defined your new ADT, yes, you have to worry about what is the implementation view, how to implement that. Okay. So, okay, so when I say ADT, what I mean is that generally we agree on a set of operations. So we agree on a set of operations, right? Like for stack, there are standard operations that you do. Yes. Similarly, for any ADT you will define, there will be standard operations. And you can also think it like that. Suppose I can tell what are the operations I need. You can accordingly define an ADT. Okay, take this ADT, this will be the best for these operations. Right? And then you may implement that, or if it is already implemented, use that. Okay. Fine, yeah, in very short. You have an algorithm and that you want to develop using ADT without worrying about the implementation view. That is why it is called abstract data type. It's not important what is the actual data type that you are storing there. So given in a stack, it's not important whether you will be storing uh, integers or characters. It's not important if you will use arrays or linked list, but what's important, what are the operations that it will support. So fine. Now given this brief background, now let me talk about disjoint set, how you define it. Okay, so let me define it as an ADT first, as an ADT. So for that, I need to understand what is the setting in which I am actually using this disjoint set data structure. So what is the actual setting? The name says a lot, disjoint set. Okay, so we are talking about data structure where we can have some disjoint sets. That's all. So, okay, let me put it more specifically. So there are n elements, x1 to xn, okay, and they are divided into disjoint sets. Okay, then question would be how. So then you say, okay, initially you can assume each of these is a set in itself, then they are disjoint sets. They are n disjoint sets. Initially, each element is a group in itself. Now, okay, so what are the operations? What are the operations I will do? The first operation I will do, okay, I just have an element. I want to convert that into a set. So I need to have an operation that will make a set. Right? So I need to have an operation make set. It will take an element and it will make a singleton set. With X. And because you have some sets, you also need some ID. Let's say its ID will be X. Make set. Fine. Initially, you will start with all elements as disjoint things. But then, yes.
Sir, what is the ID here?
Each set should be given an ID, right? Because otherwise, how will you identify what is the set? There are n elements divided into some disjoint sets. So each set should also have an ID. Otherwise, so initially you can say, okay, the ID is X itself, the element itself, or whatever. Let's say simply just ID is X. Then you start with all things being disjoint. But then you, in your sets, you will have some elements, right? Otherwise, singleton set does not make much sense. So you want each set to contain some elements. So then you need to have two more operations. First of all, now that in a set there will be multiple elements, but ID will remain the same. So you need to find out, given an element, what is the ID of the set it belongs to. So this we call as find. Find or find set X. That is, given X, find ID of the set it belongs. Okay. And
So sir, the two elements can have same ID.
Yes, that is where, because you may have only two disjoint sets among 100 elements. So that means you need two IDs. So suppose each set has 50 elements each, all 50 elements should have the same ID. So find the ID of the set it belongs to.
But that ID can be either an integer, character, or string, right?
Yes, it can be anything. It can be anything. Right now we are just saying, okay, you will use some of the X to denote IDs, but it can be anything. And third will be, see, initially they were all distant. Now you want to put two elements together, right? So then you want to merge them. So this we call it union. Union XY. So what is that? So create a single set out of two sets containing X and Y. Okay. And the new set can have ID of any of this. Union XY, if you are given two elements, X and Y, you will find out if they are, generally you will do it only when they belong to different sets. Then you create a union. You create, then you finally make them a single set. Three operations. And a DT that supports these operations, you will call it as a disjoint set. ADT. Make set, find set, union. We also call it sometimes merge. Sometimes we also call it simply find.
Sir,
Find. Yes.
sir, union will always merge two elements only.
No. It will create a single set out of two sets containing X and Y. So
Okay.
what might happen that X is in a set that has some X1, X2, X3, X4, and Y is in a set where Y1, Y2, Y3. So when you will call union XY, it will create a single set that will contain XY and all these elements, X1, X2, X3, X4, Y1, Y2, Y3. And it will have a single ID. It will take the ID of either X or Y. It will
So,
take
sir, X and Y
Mhm.
X and Y are elements of this subset. These two subsets.
So this is one disjoint set,
Yes, sir.
and this is another disjoint set. X and Y are just elements of this.
Okay, okay, okay.
Sure.
Sir,
So
in
this is-
find set,
Mhm.
if we are given X, then we can directly say it's ID.
Yeah, we can say it's ID, but you see when what happens at this time? At this time, the ID of each of the elements has to be stored somewhere, right?
Yes.
Well, they will have the same ID. They will have the same ID. Okay, let's take an actual example of an algorithm, simple algorithm, and we will see. Okay, why do we need these operations? Like, let's take an algorithm example, and I'll take a
So can
different
you
algorithm.
redefine
Yes.
ADT also? Sir?
Yes.
Yes, sir. Can you redefine ADT once?
ADT, as I said, is an abstract data type. That means you agree on a set of operations that I want to support these operations. And I don't care too much about what is the actual data type. But with this operation, I can support integers, I can support characters, I can support addresses, whatever. Right? So I don't care about the actual data type. And right now, I don't even care about the implementation view. But you see, I'll start caring about that very soon. But here I'm just saying, okay, I have a set of operations that we are agreeing on. And this is my ADT, abstract data type. Okay, no details here, like what is the actual, am I using integers, am I using arrays, am I using this? Okay, just idea of operations. I need to support these operations. Now what I'm saying, I'll give you an example of an algorithm where you can relate. Yes, actually I will need these operations there. So let me give you an example. So example is that, suppose, so think of a social network. Social network, Facebook, Twitter, whatever. Think of a social network. So what you have, so you have a lot of people, and suppose each person has an ID, right? And this can be from 0 to whatever. So there are people 0, 1, up to some n minus 1. Okay, there are some people. So in graph terminology, we can call them as set of nodes, right? So they are all the nodes of the social network, different people, set of people. B. What else do you have in a social network? Just people?
Few people are related.
Connections. So we have connections between people. So and a set of edges. And suppose that define your E. And right now assume that, yeah, this is all undirected sense. So they are all mutual friends. I mean, not mutual friends. They are all, it's a bidirectional connection. Bidirectional connection. So fine. Set of people and set of edges that are the connections. Okay, something like maybe there are people 0, 5, 3, 12, 18, 11, 13, 19, and so on and so forth. Okay, so now there are people. So now what you are given, so you are given, what is the number of people? And each people corresponds to an ID. So you are given, okay, if you are given number of people are 100, that means IDs are 0 to 99. People are from their names, say 0 to 99. These are actual names. Just say for simplicity. And you are given some pairs of people that are actually connected. So then you are given, oh, 5 and 18 are connected, 12 and 5 are connected, 0 and 5 are connected, 11, 13 are connected, and so on. You are given that. Okay? You are given that. And what you need to find out, so your task is find the number of connected components. Like in the figure here, how many connected components I'm showing? I'm showing two connected components. This is say C1, this is C2, let's say, or 1, 2, whatever you want to write. Find number of connected components, right? And then for each person, print the component it belongs to. So fine, again, you can maybe give an identify the components and you can print, oh, this belongs to C1, this belongs to C2, so very simple problem, right? What comes to your mind? What will you do?
The DFS.
DFS.
Just to cover yourself, right? Okay. But then, yeah, so then, yeah, nothing interesting, right? Why I'm talking about DFS now. So then I say, oh, let's put an additional constraint. So additional constraint. So edges, you cannot assume anything about the ordering of the edges. Edges can come in on any order. Okay. So first of all, edges can be given in any order. Okay, it doesn't matter much, fine. But there's another problem. Second is you can't store the edges. You can only scan them once. So as this information is coming, you can only scan it once. Here, 5, 18 are connected. You cannot store it in some array or whatever. You cannot store that. And this can come in any order. Okay. Now, can you use DFS?
So we can take a structure and store in the scan which we do, we can store to which it belongs.
Oh. Yeah, what did you say?
Yes, sir. We can scan only once, right? So while
Scan
scanning,
ones means you cannot store them. Can't store these edges. You cannot store these edges.
yes, sir, but in the structure we take its ID also. I mean, we take an element called ID and we just store its ID, C1. We are not storing edges.
Right. But how will you find your connected components then? You're not given connected components. You're only given there are so many people and which IDs are connected as edges in each line. You don't know connected components right now. You have to compute the connected components. Okay. So yeah, see, this constraint is only so that you think beyond DFS, and what it means, think in terms of disjoint set data structure. Okay. So we will follow these constraints. We will not store the edges. Okay. We will scan once and yeah, not store the edges. Okay. So now let's think of an algorithm that uses disjoint set data structure. So think of an algorithm that will use disjoint set. So can you think of an algorithm in terms of using disjoint sets? You know the operations.
So whenever we first take the nodes and make set of every node.
Okay, one by one. Sure. For each x in my V, you do make set for x. So each one has a separate set now. Initially, there are as many components as the number of people, right? Then as you keep on getting information about age, you do something. So
We do union.
yeah, for each x, y in E that you get one by one, you do. So for each x, y, what you do?
Union.
Yeah. So generally we say if find of x is not same as find of y. So first find out the identifiers. If they are already belonging to the same set, nothing to be done. If they are not to the same set, then you do union x. And there's a reason for that. Okay. There's a reason for that.
And sir,
Yes.
like how we will make, means what will be the ID here? Like how we will differentiate between x and y? This means I didn't get this step. Find of x not equal to find of y. So how, means what value we will compare here?
See, remember what I said in disjoint set, each set will have an identifier. So find x, what find x does? Find x gives you an ID of that set. So x and y actually belong to a set. What is the ID of that set? What is the ID of this set? If they belong to the same set, they will have the same ID. If they belong to different sets, they will have different IDs. That's all.
Like C1,
Sir,
C2
what
means
do we have in a node? Only the index.
What do we have in a node? That will be the, that's where we will come to the implementation part, how you will implement it. It will depend on how you are implementing it. Okay. So right now, just think abstractly. That's why I'm saying think abstractly. So yes, you have a data structure where, yes, I can put some elements in a set. Set will have an identifier. Find x, what it will do, it will find me the identifier of that set. Yes, I can compare if two sets have the same identifier. If they're not, then I do a union. That's all.
Sir, how will we make set then?
Again, the implementation part. Yeah, we will discuss implementation part.
Sir, for example,
Yes.
like
Huh.
if there is x1, x2, and x3, and x1 is connected to x2, so x1 and x2 will have same set, and then x2 is connected to x3.
Yes.
So then x2 and x3 will have same ID.
Yeah,
So all three
x1,
will have.
x2, x2 will have the same ID. Yeah.
Yes, sir. So if we are asked like what are the components of x1, then how we will differentiate between x2?
Only one component. What is the ID of the set? So then you say, okay, for each x belonging to V, output person x belongs to component find x. That's all. Once you are done, you do this.
Sir, here we also assume that the two components are disjoint, right? Like in the above connect components. Sir, can you go to?
Sorry?
Can you go to the place where you draw the component? Yes, sir, here. Here, 18 and 19 should not be connected, right? Yes.
Connect component means that there is no connection between this and this, right? They are disconnected. They are disconnected, right? They don't have any connection at all. That's what it means. Is that clear? Is the problem setting clear? I know
Yes, sir.
is clear because I have not talked about implementation, but I just want to think in terms of ADT. Yes, I can do my algorithm in terms of these operations. Make set, find, union, find. These operations are sufficient for my algorithm, right? Now I see, okay. So now, how many of make set do I need? How many mix set do I need? So what will be the complexity of my algorithm? in terms of the complexity of these operations. I need how many makes it? Order n makes it plus how many finds?
Order E.
Order m, I'm just using m, n for nodes, m for edges, right? Order m, you can use E also. Order m finds how many union?
Order M, sir.
Order of
Order of m or n?
M.
M.
M. Anybody feels differently? Will there be order m unions or order n unions? Very crucial. If you just see your code, the pseudocode, you will not get it. Think about your problem. What happens if you union? If union, two sets are merged into a single set. What is the maximum number of times you can do union? If
Sir,
you will reduce at least one set.
Sir,
Yes.
sir, here the union means does not mean that we sort them elements. We can merge in, sir, one element to other set, na sir. So it will be, sir,
Right.
big of
That set is gone, right?
big
So
of one.
you started with n sets.
Yes, sir.
N sets. If you are doing a union of this and this, that means this is a single set, and then there are these sets, so there are n minus 1 sets only. That is joint sets. You're not talking about overlapping sets. Oh, this is a set.
Yes,
also,
sir.
this is a set. No, that is joint sets.
Yes, sir. So that its complexity will be big of M, yeah, or N. Which is
Big of n union.
yes, sir. Matlab, which is less, sir. Which is less.
Okay.
No,
So you are saying that way that
no, sir. No. It is big of N.
This will be big of n units.
Sir.
Yes.
Yes, sir. Big of n. Yes, sir. Means if m is greater than n, then also, sir, big of n will become, no, sir, big O of n.
Okay, let's assume general case m is generally, we prefer to write order of n rather than order of n if we can. We generally think that order of m can be larger than order of n, right? M can be order n square. So yeah. So just think simply, yes, this is the complexity. Yes. At the end, of course, you can, for doing this, you may have to do order n finds also. But since you're doing order m finds here, this is okay to do it again. Yeah. It is already taken care here. So overall, you need order m make set, order m find, and order m.
So sir, here you are assuming m is greater than n.
I'm assuming. General case, I'm assuming m is greater than n. Okay. Order m, m is greater than n.
Sir, what difference will we to make if we take m less than n, because we have not made any assumption on finding complexity?
You see, okay, so this is the general thing. This is the general complexity that you will find. This will always be true. If m less than n, then also this will be true. Whatever I have mentioned here, then also this will be true. Okay. Right. I'm anyway not using theta. I'm not using theta. So this will always be true, even if m is less than n.
So, but if it is less than m, then the more accurate will be order of m unions.
Okay, you write that. You write that if m is less than n, then it will be order m units. Fine. And then we will solve separately for the two cases. Is that okay?
Sir.
Yes.
Sir, if m is less than n, then it doesn't matter. Order of n will obviously include order of m.
That's what I'm saying, but some people do not agree.
Sir, for union, we need to see the age and we are checking whether they belong to same or not. Then we are making a union, right?
Yes.
So for each age, we are making a union if
Yes.
they do not belong to. So will it be order of m or n?
That's what I'm saying. You see, at most, how many unions you can do? You start with n sets. Each union, you are sure to reduce one set. Yes. So there can at most be order n unions. There cannot be more than order n unions.
Okay.
Because generally m is larger than n. M is generally larger than n. Okay. So this will be order of n union.
Sir,
Mhm.
sir, here O of n finds you have written outside the box. Sir, how it came, sir?
No, this was just from the output. For each x, you output the person x belonging to the component.
Okay,
That is,
sir. Okay.
I said I don't worry about it because this will be included here. Okay. Fine. So now I have to think about implementation such that this gives me a good enough complexity, not very bad. I mean, this gives me an okay complexity to go ahead with. So now I can think about the implementation. Design set. Okay, and now I know what I need to optimize. I need to ensure that this complexity is minimum. Now we can think what kind of implementation we can use. Okay, now let's go to the implementation aspect. What is the simplest implementation that comes to your mind? Can you use arrays?
So in each set we have arrays and then an ID.
Okay, sure. So I'll come to that. First thing is a single array. Single array. Suppose I use a single array. Okay. So I have an array n 0 to n minus 1. Okay. So let's say array is x. So I. So xi denotes the ID of the set that ith element belongs to. There are people 0 to n minus 1 n people. So you know where is the nth ith people? That percentage at xi, and what is the ID of the set? This is whatever value you will put the ID here. Okay. So in the beginning, what you will do, you will start with x0 as 0 and xn minus 1 as n minus 1. These are the IDs. So make set is nothing but populating this array with 0 to n minus 1. So make set. How much time make set will take for order and make set? How much time it will take?
Sir, n.
Order and time. Fine. What is the complexity of find?
1.
Order 1. Find set is nothing but find set x. You are given the ID I. You go to that xi and you output that. Oh, 1. Easy. Okay, now what is remaining is union. So what will happen here? So suppose you have 0, 1, 2, say 1, 2, 3, 4, 3. Okay, and suppose this is your x and this is your y. You want to do union xy. So what will you have to do in union xy? So first you do find set X. Okay, means yeah, you can generally you see the way we do union. Although in the code we said okay, if find set X is not same as find set Y, then you do union XY, right? But generally, when you have to do union, you already know what is the set of X and Y. So you do find set X, suppose A, and B is find set Y. Okay, and then you know, okay, if A is not equal to B, in this case, A is 1, this ID is 1, and B is 3. So if they are not the same, then you're saying, okay, you will do union XY. So what you will do actually, you will say union, you can say union AB or whatever. So if you do union, what actually you have to do?
Sir, we have to change the IDs of all the elements that have ID as B.
You can make a convention something like, okay, change ID of all elements belonging to set B to A. So all the elements that belong to set B, change their ID to A. That's all you have to do. So in this case, what you have to do, suppose your A is 1, B is 3. So anything that has 3, you change it to 1. And wherever there was 3, you change it to 1.
Sir, 1 and 3 are IDs.
Yes, 1 and 3 are IDs.
So, sir, find would compare IDs or means what will find will give?
Return you the IDs. Find will return you the IDs. So here you are given 1 and 3, right?
Okay, sir, got it.
And you are comparing them. If they are not the same, what you think, change ID of all elements belonging to set B to A, and you are doing this. Now, what is the complexity of union? Yeah, tell me.
So where are we storing the elements X and Y? Means how we will know that the position I is corresponding to element X?
See, right now we are making a very simple thing that, okay, all of these are simply IDs. 0 to n minus 1. So when I say find set X,
So we have two arrays, like one has all the values and one has all the corresponding IDs.
Yeah.
Okay.
Sir, you said that the complexity.
Don't mix up the two things. Yeah. So I'm saying each person is being denoted by the index 0 to n minus 1. Okay. And then they have an ID. So X of I gives me the ID of that set.
So, but is it necessary that all elements from 0 to n minus 1 will be as present in these sets? I mean, some positions may not be populated because we don't have that particular element.
No, here we are not taking that case. We are taking all 0 to n minus 1 people are there. There are n elements. Okay. See, this you will have to assume. Otherwise, this goes into how I can have the name of people. I can be given name of people. The ages can be name of people. What will I do? Find set at a name. So I need to have a order one way of finding out where is that person located in this array. Yes. And for that, I have to use some more techniques, some hashing and all that I don't want to go into right now. I have to use some mapping, hashing first. Right now, we have a very simple scenario where each element just is an ID, nothing else. We can do general case. You need some more tools for that. Right now, just take it like, oh, each person is just an ID, and all the n persons are present. Otherwise, it's not a difficult thing to convert that to this particular thing. Okay, by a simple mapping, we can do that. And that will be order one per person. So yeah, doesn't add any computational burden also. Okay, so is that okay if you go ahead with this assumption that we have n people right? And there are edges defined between them.
Sir,
Yes.
here the order of union is n square, right? Because for every union
That's
which
what I was asking. Yeah. What is the complexity of union? A single union. What is the complexity of union?
n square.
No, single union.
Order n.
Order n.
It's
Order
order.
n.
It's just order n, right? Because in general, I may have n elements in or order n elements in set B, and all of these IDs have to change. So this can be order n, right? So I had to do order n make set. So what is the overall complexity? N make set. M find was 1 plus n unions, so n square. So this is order m plus n square complexity. Right? That's what we obtain. Do you agree with an array? This is all we can do.
Sir, can m be more than order of n square?
No, m cannot be more than n square.
So we can directly write order of n square, right?
So we don't generally do that because we try to keep them like separate. Order m plus n square. We can write it order n square also. I agree with you. But this can also be written as order n square. And there is no harm in doing that.
Okay.
But I'm just writing it in terms of m and n separate. Yeah, this is equivalent. Okay, with an array. Now, so good. So we know what we can do with an array. Array was good, make set was good, find was good, only union had a problem. So now, what is the next? What next? What is the next thing that will come to your mind?
So like for union, we can directly take address of pointer and something like linked list.
Linked list, right? Linked list. The implementation using linked list. Okay. So here, let's see how you will implement using linked list. So how would you do make set? So that means, what do you mean in linked list? So each set will have a linked list. Each set corresponds to a linked list, right? And when you find the ID of that linked list, and when you do union, you combine two linked list. Right? So first of all, how will I do a make set in linked list? So I have a head pointer. Head pointer I can use to store the ID of the set. Now in a node, what all I need to store?
Set the value, ID, and the pointer.
Next pointer. Okay. Yeah, so I can do two things. So I think they are equivalent. We will see. One thing is that I can store the actual value, and a pointer that points to the head, and head stores the ID. Okay, that pointer to the head. Okay, and ID is stored in the head only. So that means if I have something like this.
So by value, we mean the ID of the elements stored in the set, right?
See, value can be actual value x, actual x, actual identifier for x. For ID, you are having a pointer that will point to the ID of this. That means that will always point to the head.
Sir, why we are using this back pointer?
That's a good question. Let's see what are the possibilities. Instead of back pointer, we can do something else also. That's what you are saying. And I think they are equivalent things. Yeah, I agree with you. We may not need this back pointer. We can simply store the ID. Let's see, but I think that does not make any change. I mean, that does not give you any advantage, even if you do that. They are same things. So one is that you can use the back pointers that will point to the head always. Okay. And head stores the ID. So you have the back pointer. You have the next pointer. And you have the actual value. Okay. What you're saying that instead of a back pointer, we can actually store the ID here itself. And that may be equivalent to this. That will possibly be equivalent. We will come to that. I think that will be equivalent. And let's say suppose you have a second linked list that has 3 elements. And like that there are back pointers. Okay. Let's see what I will need to do now. I have to do 2 things. One is find, another is find set x, another is union xy. So how will I do find set x? I don't have an ID like I had in the case of arrays. Yes. So what do I need to do?
Sir, we have to change the head pointer of means of y to x.
You're talking about union. So first of all, say find x, find set x. X can be anywhere. X can be say here. This is x, and this is y.
Sir, sir, I don't understand where the back pointer is pointing to.
To the head. To the head.
And sir, what does head stores?
Head stores the ID of this set.
ID, I mean the array of IDs.
No, just the ID of the set. The set has a single ID.
Okay.
Right? So it has a single ID. Head stores the ID of this entire set.
So, sir, are we making an array of linked lists?
Yeah. So, but why do we need an array of linked list?
Sir?
Yes.
Sir, while passing an just linked list, we simply pass the address of the head. So where's the need of storing it again? Like after all of them are pointing to the head, so I could just separately store head only.
See, good point. But that happens in the beginning. In the beginning, what will happen? You will create a set, you will create n sets and list, right? But then what happens? You keep on reducing your number of linked list as you do unions, right? So this is a general in between, this is what will happen. So what you need is an order one access to each element in the linked list, everywhere, so that you can do very easily. You can store this address. You can have this address, right? You can just store the address, this address that points to this element, and then you can store for each element just have an array of these addresses that will point to this element. This address will not change once you create this method.
Sir,
Yes.
sir, initially there are n elements and n IDs.
Initially there are n elements. Each of them has a head. Head stores the ID. Yes.
Sir, which means we are creating the linked list and linked list.
And linked list. Yes.
Okay. Okay.
Right?
So sir, there should be an array of the heads.
You can do that. I'm just saying that array of head. So you can use array of head, but that does not help you in long term. Because you see what you need finally in between, you may have just two linked list. So you need just two heads. So what you will do with order n array of heads, what you instead need is in order one access to all the elements. So that means you need to store what is the address of this node. So that means you need to store what is there in this, right? You need to store what is there in this element. So if you just have an array that, okay, if I'm given the value, this value, and suppose these are just IDs. So for this ID, this is the address. ID index, let me use index. For this index, what is the address? So that means for every X, I have a separated array that gives me the address to access this. So X, I know how to access this in order one, just by this address. Okay, that's all you need, nothing else you need. Do you agree with that?
Yes, sir.
Sir, you are saying that it takes order of one time in finding find set.
No. Yeah. Find set is order one because you have a back pointer to the head, and this is just order one access. So find set is order one.
But sir, to find set, we also need to go to the value, right?
Go to value. That's what I'm saying. That's what I'm saying. Given find set of X, you first have to go to this location, and that should be order one access. Because X, you can have an array that tells given an element what is the address, this address. That you can store in the beginning itself when you're doing make set, right? So you have an order one access to this element, and then you have an order one access to the ID of this element.
Sir, here we are assuming that otherwise how we will do?
What are we assuming?
Each X is itself an array index, like in the array in which we store the addresses of nodes.
It's like an index. That's what we did in the last problem also.
That assumption is still continued. Okay.
Right? Because otherwise, as I said, you will have to do some mapping, hashing, etc. So we are avoiding that right now. Simple.
Excuse me, sir.
Yes.
So we are using the back pointer so that given an X, we can find its ID in order one time.
Yes.
Okay, sir.
Sir,
there are many other ways of doing that, but they are not more efficient than this. Okay. Yeah. You can think about
we are passing only the value in the find set. So
Yes,
sir, how
the
we are
value-
converting address from the value?
Values are 0 to n minus 1. Values are 0 to n minus 1. These are your values. Okay. There is no gap. And you can have an array of size n where each element contains what is the address for the 0th element, for the first element. Okay. That address you can find out when you are doing make set. When you are doing make set, you can find that address. Store it, they will not change.
Sir, it is array and we are dealing with linked list.
Okay, you may have a class right now. If you don't, you can stay. I can explain that. If you have a class, you want me to continue this tomorrow, I can do that.
You can do this
Yes,
tomorrow.
sir.
We have a class.
Huh? You have a class now?
Yes, sir.
Yes, sir.
Okay, I think so. I'll take up this question again tomorrow. I'm sorry. I think I extended tomorrow. Then time. Thanks.
Thank you, sir.
Thank you, sir.
Thank you.